to the Radical STEM Homework Help Livestream. So, if you have any homework questions, math or science related, you can ask them here in the chat. I will do my best to help you solve them live. So in the meantime, until we get any viewer questions, I'm just going to be working on some random math and science problems just to pass the time. But just like it says there on the screen, don't hesitate to interrupt if you have a homework question of your own. Okay. Let's start with some calculus, because I always like passing the time with integrals. Okay, so secant times sine over cosine. Now, could obviously rewrite this as secant times tangent, but I'm not sure if that will help us, because suppose we tried to say let u equal secant, then du would be secant tangent, but we can't really take the whole secant tangent into the du and then still have a u left over. Or maybe we can. Would it just be the integral of du with nothing else there? I'm not sure that's going to work, so I'll try something different. Okay, so secant is 1 over cosine. So we could also call this sine theta over cosine squared. And now, I think we can let u equal cosine. Because then the derivative of u with respect to theta will be d theta of cosine, and the derivative of cosine is negative sine then we'll bring the d theta over here, and we'll bring the negative to the other side. So that should give us negative the integral of du over u squared. Or, if we rewrite that, that would be u to the negative 2 du. And then we just use our power rule. So that's negative. We raise that to the negative first, and then divide by negative 1. And since we're evaluating an indefinite integral, we get a plus c. This negative and this negative will cancel out. And u to the negative 1 is just 1 over u. So let's replace u with cosine, what we set it equal to earlier. And then one last simplification. We already said earlier that secant is 1 over cosine. So this is, in fact, just secant. And now that we've seen this, that makes me think that the other substitution we could have tried would have worked as well. Let's write that out. So if we wrote this as the integral of secant tangent, and we let u equal secant, then du was secant tangent times d theta. I would be the integral of du. So it would just be u plus c, and we said that u is secant. So yeah, that actually would have worked. So that's neat. When you can get it to come out as the same result multiple ways, that's a good sign that you have the right solution. Okay, here's what I was going to try the other night. Okay, so first thing I want to do is rewrite that cubed root as a 1/3 power, so it's a little easier to see what we're doing with the derivative. Now the question is, should we try to take the derivative first or try to integrate first? I think we want to take the derivative first, because that's going to leave an x cubed inside the derivative, but it'll also give us an x squared. And then we can do a substitution to let u equal x cubed minus 8 and have du in terms of x squared dx. So this derivative will be 1/3 x cubed minus 8. A third minus 1 would be -2/3, and then times the derivative of the inside would be 3x squared dx. So 3 and a third cancel out, and this is the integral of x squared over x cubed minus 8 to the 2/3 times dx. Now we can let u equal x cubed minus 8 so that du dx equals ddx of x cubed minus 8, and the derivative of this, here we would get 3x squared, and the derivative of this constant 8 would be 0. then we'll bring the dx to the other side. So du equals 3x squared, and we'll bring that 3 to the other side. So x squared dx equals du over 3. So our integral is now going to be 1/3 du over u to the 2/3 power. And we'll just rewrite that as a negative exponent. So that's u to the minus 2/3 du. Use our power rule. We'll raise minus 2/3 by 1, which would be 1/3, and then divide by 1/3. We have 1/3 divided by 1/3 will cancel out. And we've just evaluated an indefinite integral, so we'll get a plus c. And then our u was x cubed minus 8, so we get x cubed minus 8 to the 1/3 plus c. And this is actually kind of obvious now that I think about it. I think the point of this integral being on the worksheet that I was looking at was maybe to, you know, have unsuspecting Calc 1 students or math tutors do all of this work to arrive at this integrand at the end, and then realize, oh right, if we're taking the derivative and then integrating, we're just going to get back that same function. Of course, we do have a plus c here because of the integration. But since we know the original function up here was just that, that also tells us our plus c would be equal to 0. There's actually a lot of those on this worksheet, which makes me wonder if those are all supposed to be solved just by saying the integral of the derivative is the function, or if you actually are supposed to work them all out that way. Okay, let's try a definite integral. Oh, and that's from minus 1 to 1. So, we can just evaluate each piece on its own. So minus 1 to 1, the integral of e to the x dx, and the integral from minus 1 to 1 sine x dx. The integral of e to the x is itself the integral of sine. If you derive to positive sine, then you integrate to negative cosine, right? Because if you were regular cosine, the derivative would take you to negative sine. So you have to have a negative in front of it. So this should be negative, I'm going to say negative cosine of x from -1 to 1. And since this is a definite integral, there is no plus c. And that would be e minus 1 over e plus negative cosine of 1 minus negative cosine, so plus cosine of -1. Now we can use a fun little fact here about cosine, that it is an even function, meaning that cosine of x equals cosine of -x. So cosine of -1 actually equals cosine of +1. And if we have negative cosine of 1 and plus cosine of 1, this whole term is going to be 0. Which means that our final answer is just e minus 1 over e. This one looks like it could be fun. It's going to be from e to 2e of cosine minus 1 over x dx. So again, we'll just do each piece individually. So the integral from e to 2e of cosine x dx minus the integral from e to 2e of 1 over x dx. Now if we derive to cosine, then we're going to integrate to sine of x from e to 2e, and the integral of 1 over x is always the natural log. That's the natural log of x from e to 2e. This is why I said it looked like it would be fun. So I knew we'd end up with a natural log and some e's, so they're going to cancel out somehow. So this is sine of 2e minus the sine of e minus natural log of 2e minus the natural log of e. Now the natural log of e is simply 1. The natural log of 2e, however, is not quite as simple. If it was e squared, we could pull that 2 out, but it's not. It's 2 times e. we're going to use a different natural log fact. So the natural log of something minus another something is actually natural log of the first something divided by the second something. So this is the natural log of 2e over e. And then our e's cancel, and that's just the natural log of 2. Now for these sine functions of e, we could leave them like that. This is all a numeric value, but I kind of want to see if we can simplify it with the complex definitions of sine. Because sine of any real or complex number z is e to the I times z minus e to the negative I times z, all divided by 2i. Oh, but that's not natural logs. We would have e to the e something or other, so actually, never mind. There's not really a good way to simplify that then. So, our final simplest answer is that sine of 2e minus sine of e minus the natural log of 2. Here we go. Okay. So, one plus e to the 3x, e to the 3x plus 3x. I wonder if, wonder if we aren't supposed to factor out an e to the 3x from the top and bottom. I don't know. Let's just try some stuff. What if we factor out an e to the 3x? We would have e to the minus 3x plus 1 and 1 plus 3x e to the minus 3x. Does that help us at all? Not sure it does. In fact, I think that is maybe worse. Let's see. What if we do the classic let u equal the bottom of this fraction? E to the 3x plus 3x. Then du dx is e to the 3x. Well, it's the derivative of the right hand side, which is e to the 3x times the derivative of 3x, which is 3, plus the derivative of 3x, which is 3. Okay, yeah, that's what we're supposed to do. So now we can factor out a 3 from both of these terms. And look at that, 1 plus e to the 3x, just like our numerator. And we can divide the 3 to the other side and bring the dx over here. So now we have exactly our numerator to absorb into this 1/3 du. So now our integral, we're going to have different boundaries. We'll fill those in a second, but it's going to be 1/3 du over u. So let's see. We start with x at 0, so that would make this part 0 and this part 1. So u will go from 1 up to, when x is 1, this is 3, and that's e to the 3. So then this is 1/3 the natural log, the absolute value of u, evaluated from 1 to e to the 3rd plus 3. I confused myself looking at all these bars back to back. Just going to go ahead and fill that in right here. So e to the 3 plus 3 minus the natural log of 1. The natural log of 1 is 0. And e to the 3 plus 3 is a positive number, so this is just a regular natural log. And there we go. That is our final answer. This integral equals 1/3 natural log of e to the 3 plus 3. Okay, this one looks interesting. And is that, okay, that's an indefinite integral. Sine of natural log of a times x, all divided by x. Let's see here. So if we do a substitution where we let u equal the natural log of x, or natural log of ax, we would get 1 over ax as the derivative, which I think should help us get rid of that denominator. And it's important that a is a positive number here, because natural log is not defined for negative numbers. So that means that the derivative of u with respect to x is the derivative of natural log of ax. The derivative of natural log of some stuff is 1 over that stuff. And then we can bring the dx to the other side. And let's bring the a up to the other side as well. So a times our du will account for dx over x. Now our integral is going to be equal to a times the sine of u, du. And the integral of sine, if you derived a positive sine, you integrate to negative cosine. That's negative a times the cosine of u, and we just evaluated an indefinite integral, so we get a plus c, and then we'll fill in what our u was. So that's negative a times the cosine of the natural log of a times x, all plus c. Okay, that one looks interesting. Actually, I'm going to look for some more. Let's see. Okay, let's try this. Oh wait, no, not that. That looks terrible. Oh yeah, okay. Let's try this. So, this is an improper integral because we're crossing 0, and 0 is a number that cannot go in this function. It's undefined at 0. So we're actually going to have to split it into 2 pieces. We're going to say, I'm going to have to use limits as well. The limit of something will be from -2 to, we'll call this s. So the limit as s goes to 0 from the negative side of dx over x squared plus the limit from, we'll say, t to +2. This is the limit as t goes to 0 from the positive side of dx over x squared. The reason we have to do these limits is because, like I said, we can't plug 0 directly into this function, nor to what we're going to find out to be its antiderivative. And so once we evaluate these definite integrals in terms of the variables t and s, we're going to evaluate these limits and see if this will actually converge to a number, or if it's going to diverge to positive or negative infinity. So, in general, the integral of dx over x squared is the integral of x to the -2 dx. And that's x to the -1 divided by -1. So each one of these will be -1 over x. And then we'll evaluate it from its boundaries. So our integral is going to be the limit as s goes to 0 from the negative side of 1 over s minus 1 over -2 plus the limit as t goes to 0 from the positive side of 1 over 2 minus 1 over t. And yeah, it looks like this is going to diverge. So we could bring out the constants if we want. So that'll be +1/2. That's +1/2. And then we would have the limit. Why did I put a dividing bar into the limit? As s goes to 0 from the negative of 1 over s, and the limit as t goes to 0 from the positive of 1 over t. Actually, that's negative. But both of these are going to end up diverging. If s goes all the way to 0 from the negative side, so it's a negative number getting close to 0, this will be negative infinity. Over here, if t is going to 0 from the positive side, this is going to be positive infinity. The negative sign will make it negative infinity. So if we're adding 2 infinitely negative values, it's gonna be infinitely negative. Goes to negative infinity. So this integral I does not exist. This one looks fun. It's been a while since I've done a number to the variable power. So, the problem here, of course, is that we have an infinite boundary. So we're going to do the same thing that we did before. We can't just plug infinity into here, so we're going to replace it with another variable name. We'll call it t. Then we'll take the limit as t goes to negative infinity. Now we just have a regular definite integral with a finite number, and once we evaluate it, we'll take the limit to see if it's going to converge to a number or not. So I believe with a number to a variable power, we want to play our e to the natural log of stuff game. So e to the natural log of 2 to the x is exactly the same as 2 to the x, because e and natural log are inverse functions. But what this lets us do is bring the x outside, so this is really e to x times the natural log of some stuff, which I'm just going to call a, e to the ax dx. And if we've done this enough times, we know this is going to be 1 over a times e to the ax. So that means we're going to get 1 over the natural log of 2 times e to the natural log of 2 times x. So that's 1 over natural log of 2 e to the natural log of 2 times x, but we know that's just this, which is really just this, 2 to the x evaluated from t to 0. So that's 1 over the natural log of 2 times 2 to the 0 minus 2 to the t. 2 to the 0, or anything to the 0, is just 1. Oh, I forgot to rewrite my limit. What is wrong with me? The limit as t goes to negative infinity of, I'm going to go ahead and write 1, minus 2 to the t now we can go ahead and evaluate our limit. So right now, t is some negative number, which means could really write this as 1 over 2 to the t and say that t is going to a positive infinity. So if we have t going to infinity, 2 to the t, of course, is going to become an infinite value. And if we have 1 divided by an infinite value, this term is just going to be 0, which means that this whole limit, this part, will overall evaluate to 1. And 1 times this is just that. So our integral at the end comes out to 1 divided by the natural log of 2. That's pretty fun. I like that one a lot. Okay, we probably got time for a couple more, barring any viewer questions that may come up, which are welcome at any time. One looks interesting. Oh, I erased my I equals the integral sign. Kept it up for so long. Natural log of x over the square root of x dx, and that's going from 0 to 1. Let's see what we can do with this one. So this is another improper integral because, for two reasons actually. We both can't plug in 0 to square root of x being in the denominator, but also we can't plug in 0 to natural log because we'll get negative infinity. So we'll have to set this up with a limit as we have before. So the limit as t goes to 0 from the positive side, because we're coming from the positive side of the real number line, t to 1 natural log over the square root of x dx. Now, how do we integrate this? Could try to rewrite the integrand maybe? So natural log over the square root of x to the minus 1/2 times natural log of x. That's natural log of x to the square root of x. But I don't think that helps us at all. That looks wild, to say the least. Maybe there's some specific substitution or multiplication we can make to rewrite this integrand. if we multiplied the top and bottom by the square root of x? Would that help us? If we did this, then we could make a substitution and let u equal the natural log of x. So du would be 1 over x dx. And then what would we have for the square root of x? If u was natural log, then x would be e to the u, and x to the 1/2 would be e to the 1/2 u. Okay, we can do that. Yeah, that's the trick. So let's say I equals the limit t goes to 0 from the positive, from t to 1 of this dx, and then that equals the limit as t goes to 0 from the positive from t to 1 of the square root of x, natural log of x over x dx. Now we will let u equal the natural log of x, so du equals dx over x, and we'll note that square root of x equals e to the 1/2 u. So now our integral equals the limit as t goes to 0 from the positive. We're going to have new boundaries. When x is t, u is natural log of t. When x is 1, natural log of 1 is 0. And this is e to the 1/2 u du. We said e to a number times our variable is going to be e to the number times the variable divided by the number. So this is the limit. We'll go ahead and put the divided by a half in front of everything since it's a constant. Divided by a half is multiplying by 2. The limit as t goes to 0 from the positive of e to the 1/2 u from natural log of t to 0. So that's going to be e to the 0 minus e to the natural log of t, but it's a half times the natural log of t. So bring that half in here. It's e to the natural log of t to a half. So it's t to a half, or the square root of t. E to the 0, we should also note, is 1. Ooh, okay, that was a lot. And now, it's going to converge. There's no problem with t inside the square root function being equal to 0. We can take the square root of 0, it's just 0. So that means this whole limit will just evaluate to 1, and the integral overall is equal to 2. That was a doozy, but I like it. Okay. And it looks like we are out of time for the day. It is 5 o'clock, so if you've been out there watching, thank you for watching. I hope you enjoyed the integral hour today, because I did not do any other types of problems, but hey, I really like integrals. So, if you have homework questions next time, I hope you will be able to ask them. We'll be glad to help you solve them live here on the show. But until next time, have a radical day.